We face an ongoing issue these days in trying to ensure our living environment is healthy for people as well as a natural environment, while at the same time providing homes for people. And I would say that many years ago, I had a mayor that I knew quite well say to me once, "What do you want? Do you want fish or do you want people?" And I don't think they're mutually exclusive. And today we face a real challenge as our population continues to grow, and the sound environmental and development policies that we built over the last 40 years through good science and programs are being systematically dismantled. So we're once more dealing with the mistaken opinion that we need can either have fish or people, and it's not mutually exclusive. So in this talk, what I want to do is explore a little bit more about the impact of urbanization on natural systems. Urbanization is just one of the many perturbations that happen in natural systems. But it's probably one of the final perturbations that, especially in the South, that really impacts our watersheds and our natural systems. So I'm just going to see if I make sure this works well. Going the other way. Okay. And a second here. There we go. So this is the outline. I just want to talk about where we've come from. I want to talk a little bit about how we should be viewing landscapes planning. Context, everything, and how we look at landscapes. I want to talk about urbanization and its impact on the form and function of watersheds, and then talk a little bit about its consequences, and then where we can and have gone before, and where we can improve the way we do business. Those that know me know I love this slide. This is from the Carling Conservation Digest from 1947. And you can see this, the old young guy there back in the 1800s fishing a beautiful stream, nice forested landscape, a little fish jumping everywhere, dicky birds flying about and so on. He's got a nice stringer of fish. And there's the same young lad now, an old codger talking to his grandson saying, "When I was your age, William, a sparkling stream flowed here. What you see is the result of the destruction of the forests and the swamps." So 80 years ago, we knew the consequence of changing landscapes and the impacts of those landscapes. Why do you keep forgetting? I don't know. Another colleague of mine, Dr. Richard Hoffman. Richard is a professor of medieval environmental history at York University, now retired. Wrote a book called The Catch, which is really quite interesting about the history of medieval fisheries. But he also wrote a paper about the impact of urbanization on 12th century Europe. And in it, he gave me a call when he's working on the paper, and he said, "Hey, Jack, you keep talking about this thing called fluvial geomorphology. Is that a science?" So, "Yeah, Richard, it's a pretty well-established science. A lot of good papers on it, and a lot of good literature." He said, "Oh, okay." He said, because the monks were able to record changes in landscapes and watersheds as the city-states grew. And they saw changes in sediment load, changes in flow patterns, changes in flood flows, changes in bank erosion, and changes in fish populations and water quality. Gosh darn it. That was 12th century. And now 900 years later, almost, we're doing the same friggin' thing again. As a species, we have a real problem. Anyway, so the biggest problem we face is a piecemeal approach. We started moving away from a piecemeal approach with the development of watershed planning back about 1990-95, where we realized that land and water are not separate. They're one entity. Water comes out of the sky, usually as precipitation of some form, moves over and through the landscape, modified by that landscape, and finds its way to the lowest common denominator, lakes and rivers, and then creates an expression on those landscapes. So we do know that they're linked, but we tend to plan them separately, and we plan with the consequences. So we change the structure of these landscapes. We change the water budget, hydrologic cycle, if you will, and that changes the interaction of water with the land, nutrients with the land, animals, plants with the land. And this piecemeal approach eliminates the ability to understand the consequences of changing bits and pieces of the landscape without thinking about the broader picture. So we need better planning, and that means we need the context of understanding your system in order to plan better and at a broader scale, even though you might be implementing at a local scale. So my comment to a lot of planners years ago was, we as a society have a choice in the trajectory of that little watershed. Maybe it's deteriorated over a certain period of time, and we can change that trajectory and adjust it to a certain degree, but we require an understanding of the context of that watershed, what it can and cannot accomplish, how we put the development and land uses on that system, and which way we want to go. So we do have some level of control if we choose to decide. The other issue is that we have a tendency to something called creeping baseline. And the systems that I used to fish when I was a kid, living in Kitchener and driving out into the forests and the streams around New Hamburg, that landscape is very different now than it was when I was a kid. Those rivers and streams are totally different than they were when I was a kid. If I was a kid now growing up in those areas, I would think what I saw in front of me was normal and it was always there. It's not the case. We have our baseline changes as each generation comes and experiences changes in the landscape that has occurred from past activities. So, is there this one? Yeah, there. So my comment is this is sort of an example of sliding baseline where we do a perturbation and something that maybe makes it a little bit worse, maybe we make it a little bit better, but over time, without understanding what we could have, we slowly creep down, and every generation accepts and assumes that what they see today is normal. And that is the challenge we face with the piecemeal approach to planning. What I was trying to say is what we should look at is what's the optimum characteristics of the system that we can achieve given the situation today, and how as we work on our development, can we move the yardstick back up towards a better optimum rather than what we've got right now. And that is a challenge. So thinking about natural systems, as an ecologist, we describe a natural system by the pieces that make up that landscape, the structure those pieces make on the landscape, and how they interact, and their functions in between them. So we have a landscape, we have processes, we have vegetation, and we have precipitation and other factors moving on it, wind power, and so on. All these things interrelate on that landscape. And the challenge with ecology, this is a quote from a couple of lads from many years ago, that really ecology isn't rocket science. It's a bit more complicated than that, because there's so many damn interactions, feedback loops, antecedent conditions that all affect and change how systems behave. So if you don't have a clear understanding of some of the consequences of possible perturbations, then you may be having a real problem. And what we need to do is try to sort these things out while we try to still provide homes for people while managing for a healthier environment than we've got right now. I threw this one up because somebody said, well, you keep talking about watersheds, but there's other higher, what we call hierarchical science tools for understanding landscapes. And we have a whole variety. There's the watershed, sub-watershed, valley, site. There's the eco-region, eco-district, eco-site, eco-element. There's a biological conservation stuff, read NASA stuff, landscape, community, species, genetics. They're all valid. They're all answer a specific set of questions. The key is which hierarchy we use is based upon what question we want to answer. In the case of our landscapes where we're dealing with land and water resources, we usually use the watershed as the foundation. The reason that some of the arrows go horizontal is that sometimes a specific question arises as you're going through one of those planning processes, and you hop into the other way of thinking of the landscape to answer that particular problem. So watersheds is just one way to look at our landscapes, but it's a way where we link land, water, and critters and plants to the system. And one of the things that we're trying to do is we're trying to look at ecological planning that tells us what we should be doing based upon an understanding, at least at some level, of that landscape and the functions that are occurring on it and the interactions of those broad-scale functions on it. So when we say we're going to put something here and we're going to do this to it, we understand the consequence of that down the line, both within the site and to the broader areas surrounding that site. So the big problem we do have is that governments usually manage natural systems through policy and programs based on single issues. So the issue comes up and they create a policy to answer that particular issue. And I can still remember looking at, this is about 15 years ago when I was looking at the last set of provincial policy statements. And I looked at them and I said to one of the planners from municipal affairs, I said, at any particular landscape or watershed, half of those will be in conflict with each other, depending upon the characteristic of that landscape. So how do you sort out what is the dominant policies within the provincial policy statements to implement here? And they said, well, I don't know. I said, well, wouldn't it be worthwhile to understand how your system functions at a broad scale so that you know which policies are more important than others on that particular landscape? Oh, I guess so. So we really do need that contextual thinking. That is part of contextual thinking, understanding the context of the landscape you're dealing with, how it works, how energy and nutrients move at a broad scale, because fine scale stuff can be very complicated. But at the same time, you at least understand the direction of the system. If I push it this way, it's likely to go in that direction and have these consequences associated with it. And again, these issues are not often connected. They're quite often not connected to each other, these issues and policy statements. So we need to link them together. So we really have to embrace that idea of contextual thinking if we're really going to solve the problems we have. We thought we had that partially solved with the development of the watershed planning process. I think there's about 186 sub-watershed plans done in the province in over a 15, 18-year period. Most of those were used to help direct various types of planning related to development and homes. One of the first ones we did was with Laurel Creek sub-watershed study with Brian Turnbull, and Brian was the mayor of Waterloo. It took us 2.5 years to do it. We had a broader community group, including everybody from the tree huggers associations to the Urban Development Institute and everybody in between on that process. And we made sure that as we collected information, that information was shared with everybody, and the consequences and implications of that information was shared with everybody. After a 2.5-year period, at the end of it, everybody agreed. Urban Development Institute agreed with the decisions on how to manage the development and the watershed with the environmental NGOs, who said, yes, that's a reasonable approach. That's a great place for development. And if you do these sort of things to manage your water, you'll be able to protect these more natural areas that we think are really important. And I remember Brian Turnbull coming down and sitting down with me while the final decisions were made. He said, I can't believe it. They're all agreeing with each other after 2.5 years, because they all understood the same information at the same time and all understood the same implications of that information at the same time. There's no place to hide. So they all agreed. And when it came to updating their secondary plan to approve the Laurel Creek watershed study, it took 15 minutes of debate and they passed it, and development proceeded on the Laurel Creek watershed. So 2.5 years of time, but it saved decades of approval time for each of those developers. It saved them time in the long run and made it easier because they knew exactly what they needed to do when they put that development in to ensure the protection of that environment. But then we dismantled it, and now here we are. So, as I say, plan poorly and regret at leisure. So we do have tools, and they go from a very broad scale at the watershed level all the way down to the valley segments, down right to the site. Most of us deal at the site level, trying to sort out things at the local level without understanding what's happening at a broader scale above it and what's contributing to that local site and making it the way it is. And in order to do that, we have to sort of scale up, and sometimes from a watershed level scale down to the site level as well. And these are some examples of some of the tools that were developed and still exist in order to do that. Really quickly, just for those that I'm using the term watershed, probably the appropriate term is catchment, because usually a watershed is the dividing line between two catchments. But basically, we use the term watershed. It's an area drained by a specific river system or lake system where water that falls from the sky tends to move into that location and into those streams and those lakes. Example, Dobney Creek is a small sub-watershed of the Grand River watershed. It includes both the land and water drained by these areas, and usually the shallower groundwater systems, because sometimes groundwater can move in a variety of directions under the landscape. But this is what I consider our natural infrastructure. If we manage our natural infrastructure well, it usually doesn't damage our built infrastructure. When we don't manage our natural infrastructure well, it tends to destroy our built infrastructure on occasion. which we're seeing quite often with some of the nasty floods we've been having. So part of the difficulty with integration is trying to see that watershed from the site level. For example, when you're at the site level, you see forest, you see riffles and pools, perhaps, you see water flowing, you see the clarity, you can turn the rocks over and see what type of bugs are there, or electrofish and find out what the fish are there, but it really doesn't tell you where that's coming from. So in order to understand why you have that type of stream pattern and flow pattern with that much volume and that type of substrate, you need to go to look at the valley where the stream flows through, because that valley concentrates both surface and groundwater into that common location. But that water, the amount of water that comes in there, is being modified by the land cover, by the vegetation, which modifies the water cycle, the water budget, if you will. And that landscape plus the vegetation is controlled by climate and weather patterns over decades and centuries and millennia, which then creates a soil structure that creates the opportunity for the vegetation that modifies that water and modifies how it moves over and through that landscape into those valleys and into those streams. And ultimately, that's all linked back to the geology of the landscape. So in order to understand the site, you have to build yourself back up to understand the broader picture. And we should be doing that with our planning. So one of the things that I like to stress, especially for kids that are into ecology, is you really should take a few courses in geology, because geology does play a big role when it comes to especially aquatic ecology. It conditions the potential for the movement of water over and through that landscape, modified by the vegetative cover. It conditions the chemical makeup of that water. It conditions the potential for the sediment that you'll find in the system and how that sediment is moved and stored. It conditions the types of fish communities you're likely to find in that system. Years ago, when we were doing the Grand River Fisheries Management Plan, we were talking about Mackenzie Creek down in Six Nations. And we said, well, it's a warm water system. We can manage it for warm water, maybe even get sturgeon up there someday if we can get them above Dunnville. And somebody said, well, it's not a warm water system. I've caught trout in Mackenzie Creek. And we looked, and I said, there's only one spot where you could possibly have caught any brook trout in Mackenzie Creek, and that's where it touches the Oak Ridge Moraine in the village of Scotland. And he went, yeah, that's where I caught them. So geology does explain quite a bit about where animals can find habitat and survive. And it also creates the opportunities for other animals and plants as well to find in the system. I use this as just a way of thinking about information. So I look at the landscape and I say, okay, I need to figure out what the water budget is for this landscape. That's the hydrologic cycle or pathway, if you will. How much water comes from the sky on an annual basis? How much goes back up as evaporation or transpiration? How much goes off as surface runoff? How much goes out as groundwater or interflow? And then where does it go? How does it get down through the valley system? The other pathway from an ecological standpoint is the interaction with the river or lake in its valley. The movement of water from headwaters down means also the movement of sediments and nutrients down the system. Animals can move in both directions. It also means the interaction of the river and its riparian system, because water can flow over and through the riparian system into the stream, but during floods may be stored back into the riparian system and floodplain. And also means the river and its groundwater, because you can have actually groundwater coming out, and you can have groundwater being recharged through the stream bottom. We call it losing streams, and it can happen at different times of the year. And of course, river from the bottom end where the animals can move up and down system as well, from the estuaries and up. So that understanding those pathways and understanding the characteristics of each of those pathways within a particular watershed helps to inform what is going to happen when you look at land use change in those areas. So I consider urbanization the final blow in the changes of the system. We took those forests that were found in this landscape, those savannas and wetlands. We drained a lot of the wetlands, we cut the forests, and we modified and changed those landscapes, and we changed the hydrologic cycle, which meant we changed the water budget and how water moved over through that landscape, and it had consequences of the system. So that's through deforestation, then agricultural intensification, and now urbanization in the south. In the north would be more forestry and mining as big, and hydroelectric dam development as big perturbations. But one of the key things that urbanization does, and most of it is done so or poorly, is that we increase imperviousness, which results in a lot of things: loss of groundwater recharge and discharge. We have stormwater. We call it stormwater, wastewater. It's funny how water falls from the sky. As soon as it hits an urban area, it's now wastewater or stormwater, right? It's not a resource anymore. I find that really weird. Anyway, it's water. Well, we need water. So anyway, so we have stormwater management. We tend to want to grow out, and I don't blame kids for wanting people to want to have their own single family dwelling. But at the same time, sprawl is killing us. It's affecting our agricultural lands, and it's also meaning it's more difficult to manage our infrastructure. Also, it has a major impact on the ecology. We also have to deal with wastewater treatment, and that's very expensive. Especially, just ask Kitchener. In the last go around was at $500 million for the upgrade of the Kitchener plant. And then we also tend to want to move water more efficiently. We channelize systems. I'll talk a bit more about that a bit later. But again, this is the hydrologic cycle that I mentioned. You can see it in all these textbooks. I only learned about this in high school. Now our kids learn it in grade school, which is a good thing, as long as they don't forget it and are reminded of it. One of the other things that we noticed, this is from some work done years ago. I'm trying to remember who the heck did this, but they were comparing over time evapotranspiration in a landscape. So pre-agriculture, about up to in a temperate landscape like ours, pre-European contact, up to 65% of water they estimated that fell on an annual basis moved back up into the atmosphere either through evaporation or transpiration through the leaves and needles. Only about 35% was, and then in pre-agricultural groundwater it was about 25%, and then we had what we call through flow. Does anybody know what through flow or interflow is? Anybody a hydrogeologist here? Interflow is, and we see it on the Grand, and I've seen it on the Beaver River very well, and many other rivers. Interflow is water that infiltrates below the root horizon, and it, depending upon the soils, will run under the root horizon and then discharge back into a receiving body, or wetland, or a stream. A number of years ago, the CBC did a flow analysis during a flood to estimate how much water coming down the channel during that flood flow was from the surface water, groundwater, or interflow. They found that after a heavy rainfall event, up to 60% of the water coming out of the ground was through flow. In other words, it went in, was stored for anywhere from a few hours to a few days, and then discharged under the root horizon, being cooled, cleaned, cleansed, and neutralized. Because rainwater's slightly pH around 6, it neutralized it. It was actually alkaline when it came back out. So it modified the flood pulse. It wasn't surface runoff. In natural systems, only about 5 to 10%, or 2% actually, of surface runoff, of pre-agriculture was surface runoff, only 2%. Then we put agriculture in. Now we kick evaporation down to 35%. We kick groundwater down to 15%. There's still infiltration, but it's harder to get through the ground because of cropland and runoff. Through flow maybe increased a bit, maybe through tile drainage. And then we had surface runoff increases. But you look at post-urbanization, we go from evaporation drops down to 10%, groundwater drops down to about 10%, through flow down to less than 5%, and surface runoff is 75%. Why do our urban streams flood so badly, so quickly? It's because the water can't get into the ground, or through the ground, or around the ground, or be stored in depression storage like little wetlands and so on. So then we have a problem. So where does the water and sediments and nutrients go? Well, poor agriculture, sloppy urbanization and urban development. Then we catch all that extra water really quickly and efficiently and then flush it down the system, and we have huge algal blooms in a lot of our systems, or the river is so toxic to people or so dangerous to people during flooding, we put it into channel concrete inverts, and then in rural areas we see huge amounts of erosion, adding more sediment to the system. These are consequences. I was trying to explain to people that a lot of the issues are out of sight, out of mind. Unfortunately, I couldn't change the color on those damn things because it's a previous graphic I did years ago. But the top graphic is pre-development. You have a system that pure black would be, say, the groundwater table. And then the white is the landscape. The light blue is what I call aquatards, maybe clay particles. So it's a cross section. So you have a hypothetical one. It's got a bit of let's see if I don't know if that light will come on here. No, it doesn't want to work. Oh, here. You see a little depression storage, like a hummocky terrain. So during normal events, you get some recharge, which maintains a higher water table, and maybe more recharge here, more recharge. You have a high water table. If you have a really good hydraulic gradient, it pushes water down and creates more groundwater coming into the system. But then you put maybe a house in with a septic system and impervious surfaces, and now much of the water going in maybe has a little bit more nutrients in it. Then you have the impervious surface. Maybe you put a well in somewhere else and it drops the water table further. So there's less recharge at the top end. We're taking more water out of the middle end. We put maybe a highway down along beside the stream. Next thing you know, you have virtually no hydraulic gradient pushing groundwater towards the stream, and the stream dries up. How could this happen, people ask? We have lots of data on this stuff. We know how it happens. We just tend to ignore it in many cases when it comes to development. So what are the land use changes? What are the potential consequences of land use change? Well, this is just a simplistic way of thinking of it, but when you start changing the system, you start changing the nutrient cycling in the system. You start changing the morphology of the channel. Channels have certain patterns that they create over time, repeating patterns based upon their valley slopes, the amount of water coming down the system, and the substrate composition and the valley form. So channel morphology can change. You can have change in the amount of water that can be stored in the landscape, especially as you make it more impervious to recharge. You reduce infiltration, which means you lose groundwater. You can change seasonal flow volumes, change temperature regimes, and ultimately change habitat conditions of the system. All of these things are interconnected, not different pieces of it. So when you change these water and sediment regime and yields, these result in less infiltration and less of that interflow, which means a concurrent increase in runoff. That's why you need more of those stormwater ponds. And quite often, depending upon how well you manage your stormwater ponds, more flooding, more frequent flooding. You have reductions of groundwater contributing to wetlands in the base flow of the stream. So the stream has flashier flows, but lower lows in the summertime. You have high flow changes. You have changes in the magnitude of those flood flows, the frequency of those flood flows, their duration, and how quickly it changes. There was a study done in Toronto a number of years ago looking at a fairly intensive short period rainfall event. And the question they asked was, how quickly did the storm sewers peak out after a heavy rainfall? And it was like less than 8 minutes. So that's going from virtually no water going through those big pipes underneath your road surface to being full and fully charged. So that's how quickly it happens. You have to just go to a natural area, heavy rains happen, and maybe after an hour or two, you might see some dribbly stuff going into the river. Heavy rainfall hits an urban area with concrete and asphalt, it's already running within 2 to 3 minutes. So that's the consequence of making impervious surfaces. And all our good engineers know this stuff, and they try their damnedest to try to manage those systems. But sometimes it all depends on who's planning the project as well, and what their intent is, and how much we push for something better. It also changes the geomorphology of the valley and stream systems, as well as the floodplain riparian areas. All of these, I think of riparian zones and floodplains as the kidneys of the system from a chemistry standpoint. They can neutralize nutrients, they can modify, transform them, they can store them, they can release them in different ways. They're very important, but if we eliminate and reduce natural zones, so we were reducing our zone around wetlands and streams from 120 meters to less than 30 meters, and then now for hazard lands down to 10 meters, we have just eliminated one of the biological functions of these systems, simply because we're trying to put more development into as close as possible to make a quick buck. The only people that suffer is not the developer who got approvals to do this. It's the people that have to live there and the community that has to deal with that consequence 5, 10, 15 years later through your tax dollars. So all of these things, when you start changing that, has an impact on built infrastructure. Undersized culverts under roads, You have an extra high flood, blows out the road, costs a lot of money to repair that road. So all of these things, if the water budgets change and the flow patterns of that river change, it will have a consequence on built infrastructure, property values, and so on. All of these things occur. So the other things from a pathway, the ecological pathway disruption within the valley, is that all these perturbations can also have an impact on how animals move up and through the landscape. One of the things we find is the more we put smaller and smaller telemetry tags into smaller and smaller fish and track their movements over time, we find they move greater distances than we ever thought possible. These little minnows moving maybe 1 or 2 pools, riffle pools, maybe up a little tributary stream for a half a kilometer. They're moving around quite a bit. The larger animals moving greater distances. And sometimes they use these migration patterns when the conditions in the big river become too severe, they move in these tributaries. But if we put blockages, perched culverts perched above the stream bed so animals can't get up, we eliminate those capabilities and the animal population suffer as a result of that. We also change in-channel processes. That means the substrate composition of the system. It's what we call, and its bed load. What we say WD is width depth ratio of streams. Believe it or not, a bunch of geomorphologists and engineers years ago discovered that stable systems actually can be defined by hydraulic geometric relationships. In other words, mathematics can explain how these systems function and how they create stable patterns. And when you destabilize them, all hell breaks loose. The system will readjust and sometimes not readjust the way you want it to readjust. And also it has an impact not only on the channel structure and its bank stability, its pools, its riffles, its substrate, but that also has a consequence on the animals that live there and on the water chemistry of the system. We also then try to limit how much water goes into the floodplain. We reduce the width of our riparian systems. We call them buffers. So why do we call natural systems that are actually ecosystems in their own right buffers? You should have a buffer around your riparian system, not call the riparian system a buffer. And those loss of that riparian systems means that you're basically cutting one of the kidneys or both of the kidneys out of your body. You're eliminating the ability to capture some of the crap that comes off the landscape that's leaked out of the landscape, and you eliminate the ability for the river to transform it and make it more benign to the natural system. One of the other things to stress is urbanization has major impacts on water chemistry. I think living in Brantford, you'd understand that because you guys get your drinking water supply out of the Grand River. So anything that communities do upstream to degrade the water quality, your engineers have to figure out how to fix it so that you have clean drinking water. So urbanization has had in the past and still continues to have an issue with high nutrient concentrations. Everybody wants, not everybody anymore, but so many guys want to have a lawn. How many billions of dollars are spent on making the perfect lawn? How much fertilizer goes on? A farmer told me that in most lawns, most landowners put 10 times the amount of fertilizer per square meter that they would put on their fields. And much of that just gets washed off during heavy rain, goes into the storm sewer, straight out to your local creek or into your stormwater pond, and then into your creek. You also have that also leads to high suspended solids. You get the chlorides from road salt, nitrates from wastewater treatment plants and from agriculture, pathogens of various types, as well as trace contaminants. And of course, more recently, we're realizing a lot of pharmaceuticals. Yeah. So all of these things go into the system. And also ultimately, we also at the same time are reducing the amount of groundwater. Groundwater is cheap, inexpensive if you maintain it, and free cleansing water. It helps to clean and offset some of the nasty stuff that you're throwing in there because the water coming out is relatively clean and filtered through the gravels and sands. So it's helping to moderate and offset the negative impacts. But if you lose groundwater at the same time as you put more of that nasty stuff in, the system gets much worse, much more quickly. So what are the consequences on these changes in morphology and things on the critters that live in streams? Well, when you change the channel morphology, especially when the system starts to adjust really quickly, it tends to become simpler. You don't have riffles and pools and deep runs and such. You have wide, shallow cross sections with uniform depth and uniform flow. which means you lose all the complexity of habitat required by top-level predators and the animals that are usually top of the trophic structure in your natural system. That means you get species generalists, not species specialists in the system. So you lose your bass, you lose your trout. What you gain is lots of chubs and minnows, which are okay, but they're not the same as a more complex trophic structure. You also have higher levels of fines in the substrate, which reduces habitat complexity and eliminates the ability of the river to interact with the groundwater system underneath the stream bed, called the hyporheic zone. I haven't got time to go into that one. That's quite a complex and really interesting system. And that also means reduction in mixing and reduction in the dissolved oxygen. So all of these sort of things, including the habitat conditions and losses, all affect the biota. As well, groundwater storage affects them by that reduction of groundwater means in many cases, especially for fish like brook trout, you lose spawning habitat. The brook trout, and I'll talk about that in a few minutes, are intimately linked to their watershed. They're the early warning signal that your whole system is going to hell when you start seeing brook trout disappearing in your system, because they're so linked to the groundwater system, which means they're linked to the upper watershed, that once the upper watershed is affected, you will see it in your brook trout populations very early on. Also, temperature regimes change as we go, and all animals and plants have a very specific thermal tolerance range. And as we start moving all those those temperature ranges away from the normal long-term averages for that area, that means all those critters that require those ranges, once those ranges are exceeded, you lose those animals. So temperature increases can have major impacts. And of course, that nutrient cycling thing comes into mind. I can still remember an old friend of mine, Dr. John Plank, chatting to me. He said, okay, you got a degraded system that doesn't have a lot of complexity, so you got a very simple trophic structure, maybe 3 levels of trophic structure. So you got your algae and your diatoms, and then you have your bacteria and your fungi and actinomycetes and that, and maybe a few minnows. He said, so the system cycles those nutrients, it captures those nutrients quickly, but when those critters die, it recycles them again. So it's constantly. So if you think of a nutrient cycling as a loop, it's spiraling really fast down the system. He said, or you have a complex system with healthy environment, with a trophic structure where you have your algae capturing nutrients, algae, diatoms. Those organisms are fed on by small insects, which are fed on by bigger insects, which are fed on by small fish, which are then fed on by bigger fish. And when those insects hatch, they fly into the landscape and the birds eat them. So now you have a nutrient cycling where it's very slow and broad. He said, you have a kilogram of nutrients going into the system. What would you rather have? A couple of kilograms of algae, fungus, and bacteria, or maybe 2 or 3 2-kilogram fish? The long-term storage, if you will. So I don't think we think very much about how we manage our rivers to actually be systems that keep our landscape and our waterscape clean. But more complex the trophic structure, with the more levels in that trophic structure, the healthier the system will be and the better water quality you'll have. There's a guy by the name of Eugene Odom. Many years ago, wrote a book called Fundamentals of Ecology. He talked about the fact that degraded ecosystems leak high-quality nutrients and energy. Because he said in healthy, very robust systems, high-quality nutrients, phosphorus and nitrogen, are quickly captured by multiple types of organisms and then put into long-term tissues. Whereas in degraded systems, they leak high-quality energy. And we've seen it all over the place in our landscapes. I didn't mention we'll talk about brook trout because they're one of my favorite little critters. They are truly a watershed citizen in that they are linked so clearly to the landscape. Because they require cold, clean water, they are only found in rivers that are rich in groundwater discharge, and their spawning habitat requirements mean they need groundwater discharges, either right off the banks or upwelling, in order to spawn successfully. So as soon as we lose groundwater or modify the groundwater system, we lose brook trout. So they are, in their own right, a beautiful char. They're one of our, what I call heritage species. Very quickly, there's only 3 salmonid species we knew of in Ontario. There was Atlantic salmon in Lake Ontario. There were lake char in our lakes and brook char in our rivers and lakes. So we had 2 chars, brook trout and lake trout are chars. and one Salmo Atlantic salmon. That's it. Everything else that we have here, the Pacific salmons, the rainbow trout, are all exotics, and brown trout are all exotics from other parts of the world. So they are truly a heritage species linked to our landscape. And they require those groundwater seepages in order to incubate their eggs successfully, and that the potential volume is critical. It's not just groundwater, it's the volume of groundwater, the amount of milliliters per square meter per minute. This is a number of research done a number of years ago by one of Mark Ridgway's graduate students that found out there was a threshold associated with that, how much volume you require. You go below that volume, you may still have groundwater, but you won't have brook trout. So they disappear when those resources become sick. So just as a quick example of some work we did looking at the changes in a particular watershed. We went and did research. This is the royal we. This is something called the Conservation Success Index. We did work with the Credit Valley Conservation Authority, M&R, and federal government to try to map out the historical distribution of brook trout in the Credit River. This is roughly what they estimated from the early 1800s. By the 1850s, this is the blue. The green is where the brookies were. Now the red is where we don't have brook trout. By the 70s, it was here, and by the mid-2000s, it was there. So over the last decade and century and a half, we have lost 90% of brook trout populations, and unfortunately, see, Aaron is right about there, and they're just building a brand new wastewater treatment plant. They're going to quadruple their population, and they're going to put their discharges straight into the West Credit River, right at the border between the town and the region of Peel. So the region of Peel will benefit from their wastewater. Just coincidentally, one of the major developers on the Oak Ridge Moraine is also involved in paying for that wastewater treatment plant. Just coincidentally. So when you also look at more local streams, for example, Dobney Creek, I know is near and dear to Larry's heart and many other people here. Dobney Creek still has brook trout, and now some brown trout and a few other critters as well. And they're only there because of the groundwater coming in from the tablelands, because Dobney Creek touches the Norfolk sand plain and bits of the Paris moraine. So you have these gravels and sands providing lots of groundwater. But we could potentially lose these brook trout through changes in groundwater by impervious surfaces and by putting roads in with too many roads in those locations that affect migration and movement patterns. So we need to be very, very careful how we plan in order to do that, to do work to protect what's left of the brook trout populations in Dobney Creek. And ultimately, it's not just Dobney Creek that will be affected, but if you degrade the water quality of Dobney Creek, which is still pumping good, cold, clean water from the headwaters down into the Grand, it'll also affect the quality of the Grand, which you guys drink. So you do need to think about that. It's outside of the site level plan. This is the broader scale perspective that you need to have in order to make good planning decisions. I threw this in because this is from a paper that Ray Blackport, myself, and one other lad did a number of years ago for a DFO on groundwater and fish habitat, where we're trying to explain a little bit about circumstances. So here's an area, for example, where you've got maybe an urban development closer to the stream, but you've got the headwaters are the tablelands where you've got huge infiltration, and the groundwater table is here. It maybe has a discharge point here with a little wetland, and then it comes under the stream, underneath the ground, and pops out into this little maybe riparian area and stream channel. And maybe some of that water goes in intermediate flow and some of it in deep water. Then we go to regular urbanization, and now we reduced infiltration, we increased runoff, we built a big stormwater pond, maybe just down the bottom of the valley, rather than, and basically the water table drops and the stream levels drop, and you start to see less of a stream. However, that doesn't have to be. For one of the things that I know that the Greater Toronto area has done a lot of work on exfiltration systems, where they actually build infiltration into the servicing corridor of their subdivision. So they're actually infiltrating all through the subdivision in the servicing corridor, which is the road. That's where your other services are, your storm pipes and your water pipes and so on. They're actually looking at exfiltration. They're infiltrating, they're putting the water back into the pipes and then exfiltrating it back into the groundwater system. So that basically And there's lots of work on this stuff. This basically maintains certain level of infiltration, keeps the water table higher, maybe puts infiltration ponds further up the valley, and that eventually keeps the water table higher, and you still protect the stream. Build right into the stream, or right beside the stream. So there are tools there, well established. I think it was Stormwater Assessment and Monitoring Program of MOE that summarized a lot of this research. The acronym is SWAMP, but there are tools, and I know that the work that some of the guys did indicated that for a subdivision, medium-sized subdivision, they were able to capture 80 millimeter rainfall events with no surface discharge out of the pipes. No discharge out of the pipes, 80 millimeter, which is the frequent stuff. You still may need the big ponds for the major flows, but for the minor, more frequent ones, you can exfiltrate where the soils are appropriate. In headwaters of streams that are cold water streams, the soils are appropriate, because that's why there's so cold water streams down at the bottom of the valley. But are we doing that? We'll talk about that in a bit. So one of the key things that we have to think about is our traditional systems. Again, it's one-offs. We have one purpose, we solve the problem. We have one purpose, we solve the problem. We have one purpose, agriculture, we solve the problem by draining the channel and channelizing it. But these are all the same systems. Why can't we manage them better? Now it's entrenched. That means that now it can carry 3 times as much flood water than it did before it goes into its floodplain, which means more catastrophic flows, more higher energy, more catastrophic flows going downstream to the next property owners down below. So that is one of the issues. That's a typical situation we find with the system. So the solution then is we put more water off that we put more on certain impervious surfaces. We are very efficient at catching the water. We put it down into the channel, and the channel starts to erode the banks. Now, but people just built their houses along here. They don't want to lose property, so they demanded the community and the municipality stabilize their banks so that they come in and they armor the banks. But then the river says, well, I have more water coming down because of impervious surfaces. I need to find sediment, so it starts to cuts down, these banks start falling in, so the only solution is to armor the bed. And now we have concrete everywhere. This is what's called a logical progression based upon a flawed premise. And this is something, I don't know if anybody's ever heard of a man by the name of Dr. Luna Leopold. He was a geoscientist and geophysicist. I'll talk about him in a moment because he's the one that coined this phrase. But anyway, so once the stream is put into a concrete invert, then people think, oh, okay, we're protected from the river because we now have a nice sluice way. Now all we have to do is we can build right up to it. And they do. And now with climate change occurring, that cross-section, that channel invert was designed for specific high flow. Now we're getting much higher flows. Now all those buildings that they now built because they thought they were safe are at risk in the long term. Downtown Milton as an example. So we need to change of direction. We need a logical design evolution. This was Leopold that said this. He said, what you said is people ask engineers a simple question, because he was an engineer as well. He said, people asked us a very simple question in the 40s and 50s. How do you move water away from my lands and my buildings as fast as humanly possible? And engineers did very efficiently to protect people and their properties. But the better question was, how far do I have to move it in order to protect the built infrastructure? We didn't ask that question. So now we're starting to ask that question, how far do we really have to move it? Instead of moving it so far that now we have massive amounts of water we have to control in gigantic stormwater ponds, and then they overflow and blow out the rivers and blow out our wetlands. How do we better manage? And that's where he said you have to get back to the premise. What is the key question? And it's more than one discipline has to answer this, and we have to think about it differently. Because if you only say, I have to move all the water off the landscape as far away as humanly possible. The consequence is the design you see on the right, and which is a logical progression of trying to better and safely manage water flows, protect property, but the premise was flawed. So, why do channels degrade so quickly in urban systems? There's something called bankful flow. That's usually the one that's 1.5 to 2 year return flow in natural systems, that the river will actually adjust a cross section, its width and depth ratio, in order to accommodate that frequent 1.5 to 2 year return flow and maintain its stable pattern, its meander patterns, and its riffle pool sequence, and so on. So some of the fellows say, oh, well, that's great. So once we urbanize the system, we just have to calculate, now that we're flushing all this extra water in, what is now the new 1.5 to 2 year return flow? And they tried to build those type of systems, and they blew horribly apart until somebody said, actually, the reality is the bankful flow doesn't change, the frequency changes with urbanization. So instead of that bankful frequency occurring every 1.5 to 2 years, in some cases like Red Hill Creek in Hamilton, how often is it? Like 8 to 10 times a year. 8 to 10 times a year it has a bankful flow, which means that channel evolution occurs 8 times faster than it would under natural systems. So what do? So what we need to do is we have to change how we design channels. And that was the Red Hill Creek experiment. And it's still ongoing, and Red Hill Creek is in better shape than it was before. But it means also that because you have less of a sediment supply, you have shorter riffles, because riffles are maintained by sediment supply. When you have less sediment supply, you have shorter, steeper riffles, longer pools. But it means because you have more frequent over bankful flows, you need a bigger floodplain. You have to actually set people further back and create a new floodplain, because it's going to be inundated 3 to 5 times a year, instead of once every 1.5 to 2 years. So we can change, and these designs are there, and they're being tested. But we need to think about these things as we're working through our urbanization. So, as I said, urban systems are different beasts. Bankful does not change. Frequency does change. That's Annabelle et al. 2010. We need to infiltrate more water near the top. I don't understand how the solution is that where we have capability of recharging water, we don't bother with it. We just build everything at the very bottom of the slope. I've never been able to figure that out. Because it wouldn't be more logical if you have the soils appropriate to infiltrate as much as you can through the servicing corridor, which gets back to the question, how far do I really have to move the water to protect people's properties while still managing the water in a more efficient way? In the case of some locations, that exfiltration system works really well because it's built right in the servicing corridor, right at the top of the valley, not at the bottom of the valley. You still have the big pipes that during super heavy flows, you still may require stormwater ponds at the bottom end to catch those extra heavy ones, but the frequent events are infiltrated to maintain your water table. So we need all these things to be built in, and they have been tested in some locations that are working really well. In some cases they have to be tweaked, but the information's there. We just need to apply it. And key is, when it comes to these systems, as we develop, urbanize some of these landscapes, we need to make sure that we give the river and its valley room to move around, and room for that infiltration at the top end, and room for the higher flood flows to move into a floodplain to slow them down to low flows. We have been able to redesign some systems. Here's a little project that was done a number of years ago by Glenn Harrington and John Plank. This is a Kolb drain just outside by just across the road from Natural Sports off of Victoria Street in Kitchener. That was what they had designed originally, pre-1993. They decided to apply a natural channel design and rebuild a meandering pattern with a little mini floodplain. So that was just after they did the work in the upper left. The upper right was a year later. Then several years later, it looked like that. They had a huge flood go through that basically filled that whole valley bottom right to the top. And that's what it looked like afterwards. Everything was intact. Maybe some of the vegetation was pulled down and pushed down, but it slowed the water down, it cleaned the water up, it held the water, and still maintained the channel as it was. Still. So we can do this. We don't have to have concrete inverts, but we have to plan better at a broader scale. Even with site development here and there, that has to be integrated into a larger design in the long run, or else we pay the consequences of failing infrastructure, things blowing apart that we have to keep on constantly repairing through our tax dollars. So quick start into my summary here. So urbanization affects at various scales. This is a little document that we have from one of the papers that I put out many years ago, looking at different scales. At the watershed, headwater, tributary, what does urban development quite often do? At the valley, within the valley system, what does that mean? And at the site level, what does that mean? So the arrows increase or decrease. So watershed, at the watershed level, you increase the impermeability of the watershed. It changes the water budget, increases water yield and density. It increases nutrients, increases fines, decreases fines, and decreases inputs, and it decreases water quality. At the valley system, more surface runoff, less infiltration, lower low flows, higher fine discharges, frequent storm events, flood events. You lose channel meandering. In other words, the river doesn't go like this, which slows itself down. It goes straight like this, which increases its velocity and more damage. And at the site level, then you have habitat complexity. You lose your riffles and pools. You have a wide, shallow channel. Looks like a bottom of a gravel pit in midsummer where there's virtually no flow. And you lose water quality as well as the animal populations that are found there. So all these things happen, but they don't have to happen. So most things we do, whether it's agriculture, even also deforestation, when you start doing clear cuts, there is anywhere from a 5 to 10 year increase in water yield. In other words, floods off of areas when you clear cut a forest, but it starts to stabilize after the new forest starts to regrow. In agriculture, we keep the land in production, so we don't have that situation. We do try to, and we minimize the infiltration capability by using our drainage system, our agriculture drains and the tile drains to capture a lot of that stuff and make it more interflow and less infiltration and recharge. And we also have these other inputs there. So we do have these consequences, but they don't have to be there. The one thing I wanted to also stress to somebody once is that if you apply all the minimum standards that the province pushes to a healthy landscape, you'll end up with a minimal environment at the end, because we manage by the minimum, not by the optimum. We don't manage for the best we can get out of the system. We manage by how much we can get away with when we build something. And that's not the right way to do business. In the long run, if you want a healthier environment in the long term, with healthy environment for people, for good, healthy homes with good environments close by for their kids. So one of the things is we need to protect those recharge areas. We need to protect the valley and ensure that it maintains its stability. We have to select development locations that minimize loss of some of these watershed functions and optimize development in reasonable ways. And then we have to have standards on how they manage the water off there and how well they can infiltrate it if they can. Develop more of a distributed stormwater management system. That's that exfiltration where you can through the servicing corridor or other locations, infiltration bunkers, whatever, and maintain connectivity and flood channel. And we can do this. As a matter of fact, the province even urges us to do a better job. This is from the 2003 Stormwater Management Manual. It stresses the ministry encourages the development of innovative designs and technologies where the designer can show that an alternative approach can produce a desired result or even better. We tend to ignore that when we look at approvals. We go for the minimum. But in 2003, they said, guys, try to do better. We want you to do better. I don't understand why we don't try to do better. So we do need to promote innovation, allow for experimentation with some levels of control. Many years ago, Fred Frewer Homes said, okay, you want me to be innovative? I'm willing to be innovative if the approval agencies are willing to allow me to be innovative. We said, what do you mean? He said, okay, if I can get my consultants to come up with a really good plan that on paper and through with a peer review says this should work, are you willing to expedite my approval process and save me the carrying charges on a piece of land? I will then post a bond. The bond will be put in for 5 years post-development to ensure that the designs that I put in are working. If they aren't, use the bond to fix it. But if it is working after 5 years, give me my bond back. So he said, I'm banking on the fact that my experts can design something better for you, and I'll get my money back as well, and I'll save money on carrying charges till I get that property in the ground, and I'll get my money back if I do it well. And so we went to the Ministry of Municipal Affairs and said, this is a great idea. He said, oh, the Planning Act doesn't allow us to do that. I bet you that it does, but you just have to figure out how to get the weasel words in there. But anyway, so we are limited in some ways by the way we think as well. But what I'm trying to stress for is we need to try to figure out how to build a more enabling environment so that developers don't feel like they're the enemy all the time. But if they have got good consultants, they can design something better to get most of the things back that we want. Why not let them do it as long as we can figure out a way to post a bond to fix it if it doesn't work well, or fix it to some level. So, but if we don't do that, we're just going to be back to doing the minimum standards all the time, which we know works really well. The last thing I just want to stress is this whole issue that community is critical. Some politicians really don't want to listen to the community. I'm having those problems right now in Markdale. But I remember a good friend of mine, Steve Bourne, who's a retired professor now from the University of Wisconsin-Madison in planning, used to say true protection and restoration of natural environments will not occur until we engage those with whom we would not normally associate. This could be a sort of a rallying call for everything that's happening in the States right now. But when it comes to environment, that means that community groups that are the eco-nuts really do need to talk to folks that may not care about ecology but like to hike, like to bird, like to canoe. We need to start talking to all those groups because ultimately somewhere in there is a core of a common interest in a healthier environment for the things we love to do, in the places we love to be. So we need to engage those folks. And just to finish off, how seriously do some communities take their watersheds? Well, in British Columbia, they fast for their watersheds. A new timber cut was going to go on the Slocum Valley, and a bunch of folks went and they chained themselves to the fence, the gate going into the property. They were arrested by the RCMP, and the RCMP asked the one guy there, "What's your name?" He said, "My name is Land." They asked the gal who was there, "What's your name?" She said, "My name is Water." So Land and Water went into the Hooskow for a few days, and the rest of the community decided to fast for that watershed. Kind of passion, maybe it's kind of funny, but you have to think that maybe we need to build that passion back into looking after our local environments. Because ultimately, we can do better. I just want to thank everyone for the time to be able to have a chat about urbanization and impacts on aquatic systems. Thanks very much.
Thanks very much, Jack. I'm going to open it up to some questions on the floor. Mark Hartley back there. What's that? Okay, you're good. Oh, they can't hear it online. Sorry, Mark. Thanks, John.
Thanks, Jack. Plenty of wisdom and knowledge. And so I guess a couple of takeaways occurs to me from all of this is that, one, we know what to do. Two, we're out of time. So it occurs to me, like many municipalities have done, that if they declared a climate emergency, maybe we should declare a watershed emergency. And if so, how do we do that?
Yeah, I'm just saying that to Mark's comment that we've already seen this emergency idea happening with the region of Waterloo, who all of a sudden realized that they're out of water. Quantity, not quality. And you ask yourself, how could this possibly happen with all the research and all the modeling and all the analysis that was done? And I was chatting to a friend, Warren, and Warren said, "Yo, those reports are all there, but when I talked to the young guys in the planning departments, they'd never heard of those reports." So we have the science, we have the information. In many cases, people say, well, it's 20 years old, it can't be relevant anymore. Oh, dear Lord in heaven. But you're right. We do have the knowledge and the skill. And this is what frustrates me after, and yourself, I'm sure, Mark, after 40 years of me, 40 years plus of being in the business and working on solutions and the science behind those solutions and seeing those policies and programs built to help us address those efficiently and effectively so we still get good development, and seeing all that stuff out the door. It's as though we've got collective amnesia and we're going back 40 to 50 years. It's starting to all over again. It drives me crazy. Yeah. What?
One thing that we can do. We are out of time.
We're out of time. I think we need to basically get our communities to say enough is enough. And take not just to the local municipality, but to the provincial government. I realize as well federally that we're going to be pushing on a lot more development very quickly in other aspects as well. In my conversations with my MP, Liberal MP, about this, her comment to me was, we realize that we're going to need a triage approach to this. So we're trying to put together as many experts as possible so we can expedite the development but still have the good planning behind it. And I said, well, good luck, but at least it's something. So I think that really the province should be doing is saying, how do we triage our development in a way? And all those 180 some odd subwatershed studies are relevant from the standpoint the geology hasn't changed. The hydrogeology hasn't changed. We know where the water goes in the ground. We know how it gets out into the system. It's there. We just have to pull those damn reports out and start using them.
Thank you. There are two questions that are online. One is from Rob, and he asks, what role can beaver play in stabilizing a disturbed stream?
One beaver or many beavers? No, just kidding, Kevin. Beavers can apply. Beavers are valley builders, and they are able to retain and can hold water in the landscape. Historically, we likely had most of our beaver populations were probably closer to the headwater systems because the larger rivers were probably densely forested and managed as forest. So we may have had bank beavers here and there, but vast majority of the areas when the surveyors first came, the massive wetlands, many of those were maintained by beaver or extended by beavers. And we then clear those wetlands, took the beavers out, entrenched the systems, and now we have more water coming down the system faster. So beavers can help by regaining and rebuilding our water tables. Thinking about Alberta, that big flood they had in 2013, basically there was nothing holding it back from the foothills. The foothills have all their foothill streams are entrenched. You can drive, if anybody driven 22X from Calgary down to the Crow's Nest Pass, you drive along it's huge big hills, and you look down in the valleys where these streams are, you see these straight line streams all entrenched, banks falling in, and beside them you can see green meandering scrolls, the original stream channel. And what happened was when they took the beavers out and they put the cattle in, and the cattle cropped down those areas so much that there's no vegetation to hold the banks, the stream entrenched. So now they're using beaver dam analogs in Alberta to rebuild these channels, to start the vegetation coming back, which will are starting to bring the beavers back into those areas. And what the ranchers are finding is the water table comes up, there's more grazing land, and they're actually now gaining more grazing land because of the beavers than they would have lost by having a bit of water on their landscape because of the beavers. So beavers have a role to play. Many beavers in a small section can create a big wetland and swamp, and if you have urban or rural subdivisions, it may create a problem. And the other problem we have, of course, is we don't have the natural predators of beavers left on the landscape. So beaver populations can expand, and when we clear cut an area, what comes back is perfect food for beavers. So we maximize beaver production in some of those areas, and that's what's created a problem, but not an insurmountable problem. So beavers have a role to play, a big role to play.
The question is from Lindsay, and she asked, what would your recommendations be to Oxford County, who have approved 2 developments and another in the works on the Long Point Regional Conservation Authority's floodplain?
What could I offer as a solution? Cancel development. Yeah. That's a good, well, and the only thing I can say is that the facetious thing I would say is just wait for the next flood and sue the buggers. But that probably doesn't help very much. I would say that the Conservation Authority is remiss, and they still have obligations under the Conservation Authority Act to properly manage their floodplains and to keep people out of the floodplain. Just as an example, but people say, well, nothing's ever happened since we have conservation authorities, so why do we need conservation authorities? It's sort of like after vaccines, we didn't have measles anymore, so why do we need vaccines, right? Back in 1993, 94, a major storm system came through southern Michigan and southwestern Ontario. And a couple of the hydrologists at the CCIW decided to work with the USGS guys, and they identified and mapped out all the little sub-watersheds that were affected, both in Michigan and in Ontario. They divided them up and tried to pair them up based upon basic geology, soils, and land use. And then they compared what was the damage from that heavy, consistent storm in Michigan versus Ontario. The only difference being in Ontario, we don't allow active development in floodplains. In Michigan, it was a $480 million event. In Ontario, it was a $2.5 million event. And as far as they could tell, the only difference was that we manage our floodplains.
That was great, Jack. Thanks. So you've talked about what to do going forward with more development, but how do we fix the problems that we've already got?
Well, that's why I showed cold drain. We can fix them. As a matter of fact, I think Kitchener, I'm trying to remember the little creek that Bill Annabelle worked on this one with the city. There was about 3 kilometers of little concrete invert, I think it was on Fisher Hallman, and he basically took all that out and rebuilt it into a riffle pool, little meandering channel adjacent to the highway. And it's been perfectly fine ever since. So we can do it, but the cost of retrofitting these things is outrageous compared to not buggering them up in the first place. And that's the old adage that if you spend a dollar now, you save $1,000 later does come to mind. But the trouble is that in the short term, we like to just spend the dollar and not worry about the $1,000 that somebody else has to pay in the future. But we have done the Natural Channels Initiative, which is not just about the channel, but it's riparian zone and floodplain and corridor, has been able to demonstrate that we can design better, and we have designed better. It's not as though this is new science. And the wonderful thing about channels, because the fact that they're driven by physics, the structure of the channel, is that you can actually mathematically calculate how to bring them back into health and design them that way. So it's not as though it's magic. It's hydraulic geometry comes to mind. We can do these things. And we have demonstrated across Ontario and elsewhere that we can do these things. We just have not deemed it important enough.
Thank you. Thank you for your talk. With urbanization, you get more sewage.
Mm-hmm.
And I'm a farmer, and we're organic farmers, but we watch sewage sludge being put on farmland. People don't know what they're eating, but anyways, are drinking. So there's the pharmaceutical issue, there's the heavy metals.
Mm-hmm.
I just wondered if you'd address that.
I would like to say I'm an expert on that, but I am not. So anything that I would say is probably going to be dangerous, but it does worry me. I realize that we have a lot of waste that we need to deal with. And the solution so far, one of the solutions is to put the slurry onto farms and grow things. But I do worry about it. That's probably why I spend most of my money on organic food.
Traditionally, building has always been closer to a watershed because of, proximity to the water, the energy levels to bring it up. I think a few years ago, in the Middle East, where water is such a scarce resource, they are still building it way away from the watershed, and they prefer to transport it, both fresh water and wastewater, incur the cost, but away from an oasis or high water table, or water table somewhere in the desert. You think something like that would come here in Ontario as well?
It likely would not be a bad idea. When we did the Laurel Creek study, we identified tablelands of clays and silts of course, good farmland. As if they had to develop, that was a better place to develop. The lower areas where the water was gained into the valleys, we created what's called a level 2, which was small nodal developments with huge green space around to capture and to utilize that water and to allow it to dissipate, and then corridors of life with the active channels and with big buffer strips around them. So we were able to identify it, but definitely the development was well away from the active water areas where the water discharged and where the water gathered. That's not so much the case right now. I'm dealing with at least one, maybe two developments right now in the Markdale area. Chapman's Ice Cream, which I love, is in Markdale, and they're growing, and as a result, they have to build more homes for the people that are going to come to work there. And the Rocky Saugeen goes right through Markdale, the north end of Markdale. And now I'm looking at development going right beside the river, above the river a little bit, but all the storm water going to be dumped at the very bottom. So everything comes off the top right to the bottom, then goes into the last remaining high quality large brook trout cold water stream we have left in southern Ontario. So we've been having a lot of time with the mayor and council and with their staff saying, the reason you have so much groundwater is because it's infiltrating on all these tablelands. If you're going to put development, which you've approved, in these areas, use the exfiltration systems and put the recharge through the servicing corridors and use your big ponds at the bottom end only for the big events, and then have a weeping tile system out there that goes down towards the stream so you get further scrubbing of water and cooling it before it gets to the river. So we're still negotiating that right now.
Thank you. You mentioned that you have to consider entire watersheds, but a lot of those decisions are borne out on the site, like in each thing. A big part of development applications is pre and post drainage scenarios or infiltration. I was just wondering how that satisfies your concerns, because infiltration is a big part of the solution. And is all infiltration created equal? Like, obviously a nature-based solution is preferable, but yeah.
Yeah, of course, not all infiltration is created equal. It depends on the superficial geology and the soils in that area. For example, Daubney Creek, you're on the edge of the Oak Ridge, the Norfolk Sand Plain and the Paris Moraines. It's all gravels and sands. You can infiltrate. As a matter of fact, you have to work really hard to stop it from infiltrating, which some guys are really good at doing with asphalt and concrete. So, but in other areas, for example, where you have tills and clays and loamy material, it's a little bit different. But they've tested exfiltration on those systems. With a tweak in the design, they were able to actually hold the water between the two drop culverts, the multiple drop culverts, and hold it and then allow it to recharge back into the pipe. And they actually slowed down the flood flows by about 6 to 10 hours. Instead of 15 minutes, 6 to 10 hours, where it got cleaned and slowed down. That was even in tilly, clay, loamy soils. So we can do it. It's different designs. And my comment is that engineers are up to the challenge. We just have to allow them to do the design work and the testing that we want. Right now, we don't urge them to do that, and the developers don't urge them to do that because the regulators don't urge them to do that. I can still remember John Plank telling me when I was working for the provincial government, you guys are the problem. I said, what do you mean I'm the problem? They said, developers. He said, the developers will just take the easiest path. If they bring an innovative design to you and you say, oh my God, it's going to take me an extra couple of years to approve it, that costs them more money, even though it might be better design. So instead, they're going to go with the design that they know you'll approve, even though you know that it won't work well, but everybody else does it. I went, holy shit, he's right. So we really need a rethink, which means we need to get the politicians and the senior people to realize we can do better and allow the developers and their consultants to design things that we would like to see rather than the things that we will accept because everybody else accepts them as the minimum.
It's from Andrew McCammon, and he has a comment. You know, Ann? He said, rather than declare a water emergency, I suggest we focus on watershed security, and provides a link to a site, Watershed Security Project updates from the Ontario Headwaters Institute.
I think the issue of water security is the core. And once you get to a point where you have to declare a water emergency, you've failed in your ability to secure your water supply. And Andrew was quite correct in that. Andrew is the CAO for the Ontario Headwaters Institute. I sit on his advisory board as well. And he's quite correct that water security is important to all of us. The best way to do water security is on a watershed basis, but you don't have to do it on a watershed basis, but it's the one that makes the most sense. And you can, to the other gentleman's point, you can reduce the size of watersheds down to subbasins, subwatersheds. Dobney Creek is a small subwatershed of the Grand River. The Nith River is a larger subwatershed of the Grand, but you can divvy them up. Laurel Creek is a smaller subwatershed of the Grand. So you can separate it out and work there, but you still have to link it up and link it to the other ones.
Well, thanks everybody for coming. Thanks, Jack. Hopefully everybody's drive is good going home. And thanks again for joining us.